Okay, this is 2.2, limits involving infinity. We're going to determine infinite limits from the left and from the right. So example 1, determine the limit of each function as x approaches 1 from the left and the right. So I have two functions here, or the graphs of two functions. So I'm going to do A first. They want us to pay attention to x equals 1. So here is x equals 1. So from the left side, which would be all of this is the left, right? As I travel along the graph, the closer I get to x equals 1, the function is going up. It's headed up towards positive infinity. So the limit as x approaches 1 from the left is going to be infinity, positive infinity, which is not a real number because we don't know what infinity is. But that is a proper answer. Okay, so from the right side, and then all the stuff over on this side is the right side, right? As I travel on the graph towards x equals 1, it's also increasing. So the limit as x approaches 1 from the positive side of this function called f of x is also positive infinity. These are the one-sided limits. If they had asked us for the overall limit, just a regular old limit as x approaches 1, not specifically from the right or from the left, then the limit would actually still be infinity because these are the same. But infinity is the same as saying does not exist. Okay, there is no limit here. Infinity is the definition of no limit. Limitless, right? Okay, B should be the same idea. Here's 1, right? The left side, here's the left. So as I approach 1, the limit as x approaches 1 from the left is still positive infinity for this equation, or this function, because it's going up to infinity and beyond. Now for the right side, which is all of this right here, this is the right side. The function appears to be moving towards negative infinity. It's going down. So the limit as x approaches 1 from the positive side of this function is negative infinity. And the overall limit here would definitely just be does not exist, because one part of the function is moving up to infinity and the other part is moving down to negative infinity. So the overall limit would not exist if they had asked us. I'm very aware of the fact that they didn't ask, but I'm still telling you. Okay, next. So here we have horizontal asymptotes. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity, so this is new, right? Even though I'm sure you did it in pre-calc, but the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. This is saying that if the limits are these values as x approaches infinity or negative infinity, then that line b is actually a horizontal asymptote. So to that end, in order to find limits at infinity or approaching infinity or negative infinity, all we have to do really is find the horizontal asymptote, and that'll be the limit. So using the degrees, or the highest power, and I mean exponent, you know, like squared, cubed to the 4th power, like that, of the numerator and denominator we can determine the equation of the horizontal asymptote. Now, obviously, this only works really with rational functions, right? A rational function is a fraction. So this is me trying to make a shortcut. Now, before I start reading or trying to interpret all of this information here, take note of what's over here. It says coefficients A and B are any real numbers. Okay, so that means that these letters A and B, they're just numbers because they're coefficients. And then the letters that represent the exponents, M and N, they're positive integers. And I want you to see that M is bigger. It's the bigger number. And N obviously would make that, it would make that the smaller number, right? Okay, so now back to over here. So when, I'm going to start with this one here, f of x equals a times x to the m divided by b times x to the m. So what this is saying is when the degrees or the exponents are equal, so the degrees are the same, in order to find the horizontal asymptote, all I have to do is look at the coefficients, the numbers in the front of those degrees, of the highest degree. In this case, it's a and b. So then y equals a divided by b. That is going to be my horizontal asymptote. And once I figure out what the horizontal asymptote is, then that is actually my limit. Okay, so it's a ratio of the leading coefficients. All right, next. When f of x is a times x to the n over b times x to the m, then the horizontal asymptote is y equals 0. That's the equation of the horizontal asymptote. But that'll also be my limit. This one I like to call bottom heavy. And the reason for that is because the degree on the bottom is bigger than the degree on top. So when it's bottom heavy, the horizontal asymptote will be y equals 0. And therefore that is the limit. 0 is the limit. Okay, last one is this one right here. Here we have f of x equals a times x to the m divided by b times x to the n. If you look here, the degrees, the bigger one is on top. So if I call the last one bottom heavy, I'm going to call this one top heavy. And in this one, there is no horizontal asymptote. So since there is no y equals, it's a none. The limit is also none. Does not exist or none. They're both valid answers. Okay, now we're going to actually do some problems. Okay, example 2, finding horizontal asymptotes algebraically. Says find the limits at infinity by finding the horizontal asymptotes of each function. So here I have to find limits. But the easy way to find the limit at infinity, or in negative infinity, is to determine the horizontal asymptote. By the way, I will probably write horizontal asymptote most times like this, just abbreviated. Okay, so it's not me just saying ha. Right, A, the limit as x approaches infinity of x minus 1 divided by x squared plus 5. Okay, so I'm going to look at the exponents, the highest exponent. The highest on top and the highest on bottom. So in the denominator, obviously, I have an exponent of 1. Or sorry, in the numerator. And in the denominator, I have an exponent of 2. So this is what I like to call bottom heavy. Right, the bigger exponent is on bottom. So whenever our function is bottom heavy, then the horizontal asymptote is located, horizontal asymptote is at y equals 0. And finding limits at infinity is the same as finding the horizontal asymptote. Therefore, my limit is 0. Okay, these are supposed to be easy as long as you know the 3 rules. B. So I'm going to look at the highest degree on top and the highest degree on bottom. So I've got 2 and 2. They're equal. When the degrees are equal, then all I have to do is take a ratio of the leading coefficient, which basically means the number in front of the coefficient in front of the variable with that highest degree. So here obviously would be 6 and 4. So my horizontal asymptote is located at 6 over 4. That is my limit. Of course, we can simplify. C. Again, looking at the exponents. Okay, so on top, I've got a 3, and on the bottom, I've got a 1. This is top heavy. When it is top heavy, there is no horizontal asymptote. So there is no limit. So therefore, there is none, does not exist. Okay, D. Looking at the highest degrees, here's 2, here's 3. So this is bottom heavy again. And therefore, that means the limit is 0. So that's how you determine limits algebraically at infinity or negative infinity by using horizontal asymptotes. And of course, it mostly just works for rational functions. And a rational function is basically just a fraction. It has the word ratio in it, right? So like something over something. All right, next. Next up, vertical asymptotes. Vertical asymptotes can give us an idea of whether or not there is an infinite limit. So we have to know, or we have to learn how to find vertical asymptotes. So the line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit as x approaches a is positive or minus infinity from the right side, or the limit as x approaches a from the left side, f of x equals positive or negative infinity. So we know it's a vertical asymptote if the limits are infinite as it approaches that value. So the other way around would be if there's a vertical asymptote at that value, then the limit is going to be infinity or negative infinity. It doesn't tell us right out which one, but at least we'll have an idea. Oh, there is an infinite limit there. So example 3, finding vertical asymptotes algebraically. So first things first. To find a vertical asymptote, you only really need to look at the denominator. The denominator is where all the good stuff is. That'll give me an idea of whether or not there is a vertical asymptote. But I need to actually figure out first, before I do anything with the denominator, can the equation be factored out? And if so, I need to do so. These examples, neither one can be factored out, but the next example you'll see that it can be. Okay, so I'm going to dedicate my time to here, the denominator. And what I'm going to do is I'm going to take the denominator and I'm going to set it equal to 0. And whatever x value I get out of here, that is the location of a vertical asymptote. You could do this whichever way you like. I'm just going to go ahead and distribute. Okay, so I'm solving for x. I'm solving to get x by itself. So subtract 2 from both sides and divide 2. So x equals a. This is the location of my vertical asymptote, so therefore there is a vertical asymptote, just like ha. This is not just va. This is vertical asymptote at x equals -1. So if they were to ask me to find the limit at, or as x approaches -1, this would give me an indication of, oh, it's going to be infinity or negative infinity. B, same idea. I already said that these can't be factored, but I'm going to focus on the denominator, and I'm going to set it equal to 0. So add 1 to both sides. I get x squared equals 1. I need to get rid of the x squared, the squared part really. So square root both sides, right? Square root, and I get x equals, and the square root of 1, right? Which is 1, but it could have been positive or -1, right? Because -1 times -1 does equal +1. So therefore, I have a vertical asymptote, or I have vertical asymptotes at x equals 1 or and -1. So that's how you find vertical asymptotes. Okay, all you got to do is set the denominator equal to 0 and solve. Okay, set the denominator equal to 0 and solve. Okay, example 4, a rational function with common factors. Here it says determine all vertical asymptotes of the graph of f of x equals x squared plus 2x minus 8 over x squared minus 4. Okay, so this graph actually does have common factors, or this function. So I have to factor those out before I look for vertical asymptotes. I'm going to write a note here. So please make sure to write it down. Okay, so here's a note. Please make sure you write it down. Sometimes the function has holes in it, so you have to factor those out first. Then you're going to set the denominator equal to 0. So I'm going to look at this function, and I'm going to factor it best I can to make sure I get rid of anything that cancels out. Okay, so on the bottom here, I have a difference of squares. So x minus 2 and plus 2. On the top, I got to do it the old-fashioned way, right? The way I do it is the a times c, then b, and then two numbers. So a times c is -8, b is 2. I need two numbers that multiply up to -8, but add up to 2. So 4 and 2, they definitely add up to 8, but I need them to add up to a positive 2, and one of them has to be negative because the 8 is negative. So the 2 is going to be negative. So I have x plus 4 and x minus 2. So now I see that the x minus 2's, they're going to cancel each other out. So what I have now is the limit, or sorry, I'm not looking for limits. My bad. What I have now is x plus 4 over x plus 2. So this is the simplified version of this equation without the hole in it. Okay? This right here, this is the hole. There is a hole at x equals positive 2. Okay? So now I'm going to do the good old take the denominator, set it equal to 0, and that'll be my vertical asymptote. So there's a vertical asymptote at x equals -2. Okay. Example 5, determining infinite limits numerically, right? Numerically means with a table, no graph, no algebra. Algebraically, though, I can tell you right away from looking at the function that there is a vertical asymptote. And the vertical asymptote is located at x equals 1. And from looking at the degrees, this is a top-heavy function. And from looking at the degrees, I can tell you that there is no horizontal asymptote. But that's algebraically, and we're supposed to be doing this numerically. So we got to pick some values. So I'm going to pick some values. I'm going to pick numbers that are smaller than 1 and numbers that are slightly bigger than 1. I'm going to fill that in now. So I picked my numbers. Obviously, all the numbers to the left are smaller than 1, and all the numbers to the right are slightly bigger. And then you can use a calculator to calculate these quickly. But of course, if you had to, in a pinch, you could do this somewhat manually. It would just suck a lot, a lot. So anyway, I'm going to fill in the table. These are the numbers I used, of course. So these are the numbers I got when I plugged them in. So now we look at these numbers and we analyze the table. If you look, the numbers on the left, they're actually increasing without bounds. It's just really increasing quickly. If you look at the numbers on the right, they're decreasing rapidly, also without bound. This is a phrase we use when we're talking about infinity, without bound, no boundary. So from observing the table, I can see that the left-hand limit is headed towards positive infinity, but the right-hand limit is headed towards negative infinity. So what is the limit of this function? It does not exist because it's infinity, but also they're even like pointing different infinities. Okay. Okay, special trig limit. Here's another one. But this one, although it looks familiar, you got to pay attention to the x that it's approaching. It's approaching infinity. So since it's approaching infinity, sine of x over x is going to equal 0. Here's a picture of what the function looks like on a calculator. As you notice, it kind of just hovers around this line, which is, of course, y equals 0. And it does that infinitely, in both directions, all the way around. It just hovers over and over and over again over y equals 0. So the limit is just 0. And this is called oscillating behavior. This is not the first time, or sorry, this is not the last time you'll hear that. So we're going to go ahead and do example 6. Okay, example 6, I'm finding the limit as x approaches infinity of 7x plus sine x over x. So again, special trig function. I want to use this dude right here. So somehow I need to make this function kind of look like that one. And the best way to do that is to split it. Split it up. I can change this to 7x over x plus sine of x over x. I didn't change anything. All I did was, well, since they share the same x, I wrote it out. So now 7x divided by x, the x's cancel, so it's 7. And then sine of x over x, that's the special trig limit here, with our limit as x approaches infinity, and that's 0. So my answer is 7. And that's that. Please do your homework.